for Ampere's law, there's a couple different cases that we'll look at. Ampere's law is kind of a general law that applies to a sort of a bunch of different things, but for this one, we're looking at Ampere's law for a straight wire. What we're going to do is we're going to use Ampere's law, this equation here, and it's kind of given what things are there. We're going to use it, and then we're going to use right-hand rule number 1 to kind of figure out the direction. Okay, so let's try this on a real equation. We've got two parallel wires. They're 20 centimeters apart. We've got a current for wire A, current for wire B. They're both going, let's call that north. Okay, so both currents are going north. Excuse me. There's a current running in the same direction. Yeah, find the B field, the net B field, or the combined B field, 5 centimeters from wire A. So right here in this location, we're looking for what is the B field, the total B field. In order to figure that out, we're going to have to kind of say like the total B field is the B field due to A. Remember, these guys are vectors, plus the B field due to B. We're going to have to find those. So what we're going to do first is just say, what is the B field due to A? We know that the magnetic field is equal to mu naught I over 2 pi r. Okay, so this is going to be B field for A is going to be mu naught. Remember, mu naught's just that constant. Mu naught times I. Current A is 15 amps over 2 pi. And R, how far away? This is RA, 5 centimeters, 0.05 meters. And let's see, we put that in and we get 6.0 times 10 to the minus 5 Teslas. Now, before I can kind of say, here it is, it's a vector, I need to figure out what direction is this thing in. Okay, so we're going to pull out right-hand rule number 1. You're going to point your thumb north, again, kind of north being up this way. Point your thumb north in the direction of the current that A is carrying. You got to use your right hand for this. You're going to wrap the fingers for your right hand around wire A. And what we're going to see is it's going to go into the page on this side and it's going to come out of the page on this side. So it's going down sort of east of the wire, and it's coming, I guess I should say it's going into the screen east of the wire. It's coming out of your device's screen to the west of the wire. Okay, so that is the B field due to A. And at this location, this is the one that I care about, it's going into the screen, your device's screen, or into the page is what we often say. We're going to do the same thing for B. Okay, so let's stick a little line here. We'll kind of say next step. So we've just found this guy. We got to find this guy as well. So B field due to B is what? So B field due to B, again, mu naught I over 2 pi r. B field due to B is mu naught. Mu naught is 4 pi times 10 to the minus 7. Okay, so just in case this thing right over here, just in case you're like, how is he doing these calculations? Here it is. It's 4 pi times 10 to the minus 7. We could have put that in on this one over here as well. Okay, so that's how I got that number. So there's mu naught. It's just a constant. This is current B. Okay, so this thing over here. Wire B has 20 amps, so this guy is 20 over 2 pi. Here's the big trick, right? RB is 15 centimeters, right? Just 20 take away 5. So 0.15 meters. And BB, if I multiply all that stuff out, I get 2.67 times 10 to the minus 5 Teslas. And again, we got to figure out what direction that's in. We're going to use right-hand rule number 2. Again, you're pointing your thumb in the direction of current B, so north. You're wrapping your fingers around wire B. It's got to be your right hand. Your fingers are going to point into the page to the right of the wire. So there's BB. And out of the page over here on the left, which is actually the spot that we care about, BB. This one here is coming out of the screen or out of the page. Last step then, red, oh no, let's go black, that's easier to see. B total then is just BA plus BB. Again, these things are vectors. We got to include any vector directions here. I'm going to say, let's see, I'm going to say into the screen is my bigger one, or into the computer screen, into your device's screen, is the bigger force. So I'm going to say this direction is my positive direction, if I can say it like that. So when I sub these values in, this number here, I'm going to put as positive. This direction then, this out of the screen, is my negative direction. And let's squeeze it right down here, B total. We add that stuff together, we're going to get 3.3 with sig digs times 10 to the minus 5 Teslas. And that's into the screen. Again, into your device's screen. And there is force. Hopefully you can kind of see that. There's your answer. Find the net B field 5 centimeters from wire A on the line connecting the wires. So right there at that location. Oh yeah, and there's the answer, which you can't see, but anyways, there's the answer. 3.3 times 10 to the minus 5 into the screen. Or into the page. Second one we want to focus on is Ampere's law for a solenoid. A solenoid is like a coil of wire, like a slinky or a spring, something like that. So for a solenoid, we have to use right-hand rule number 2 for the direction of this one. Again, equation is there. You can look at it, and kind of what everything is sort of listed down here. Let's go ahead and use it. Oh yeah, page 411 of your textbook, there's a very elegant derivation. Physicists love elegant derivations if you want to check that out. Let's go through this one here. We got 2 parallel conductors, 2 parallel wires, both carrying current. They're given the distance apart, so they're this long, they're this far apart, but the current here is in the opposite direction. The question here is find the force on each wire. Okay, so a couple things with this. You could say, if we were to focus on wire 1 for a second, the current is flowing up that way. That is 4 amps. Okay, so we got 4 amps of current going up this way. I want to look at the B field due to wire 1. B field we know is mu naught I over 2 pi r. And I'm going to call this I1 because we do have 2 different currents going on here. We could sub in some numbers here, and we will in a minute, but we could sub in some numbers here to figure out what the magnitude of that B field is anywhere that we want, so whatever location we want, whatever R value. Where I'm concerned about it is this far away. So the B field due to wire 1 over here, where wire 2 sits. Because I want to know what strength of B field does wire 2 sit in. Okay? The distance then is going to be this, so the R value that we're going to sub in there is going to be this 0.1 meters. I'm going to pull out my right-hand rule number 1, first of all, and this is not the solenoid one that I was kind of showed just quickly on the screen before, but for this one here, right-hand rule number 1, thumb points in the direction, so again, let's stick a little north direction here. Thumb points north, because wire 1's current is going north. Right hand, your fingers go around the wire, grasp the wire. So it's going in over here. This is the B field due to wire 1. The B field due to wire 1 would also come out on the other side of wire 1, but I care over here where wire 2 sits. So wire 2 actually sits in wire 1's B field. That means it experiences a force. And you could say the force that wire 2 experiences is given by this equation, ILB sine theta. So wire 2 carries that much current, whatever wire 2's current is, still 4 amps, but it sits in wire 1's B field. Okay, so this is kind of important. For the force, if you're looking at the force on wire 2, it's wire 2's current here, but it's somebody else's B field right here. Okay, so wire 2's B field doesn't put a force on wire 2. Wire 2's B field puts a force on wire 1, and wire 1's B field puts a force on wire 2. It's like they're pushing each other or pulling each other or something like that. So I'm going to go ahead and take this equation right here. Let's call that 1. This equation right here, call that 2. And I'm going to sub 1 and 2. And you could do these two things separately, right? We could sub into this equation down here, find the B field, and then sub it into this equation. Way cooler, of course, always to sub in equations into the other, one equation into the other. So IL, here's B. B is mu naught I1 over 2 pi r. And we still have our sine theta there. Okay, so there's kind of the big equation. We typically see this thing rearranged. So the force on wire 2, people often put mu naught out front. People like constants out front. I1 and then I2. Okay, so there's this guy and this guy and this guy are taken care of. We still have an L out here, and then all over 2 pi r. And then there's sine theta here. Something to notice with this sine theta, the B field due to wire 1 is directly into the page, whereas the current is going south, according to my sort of setup here. That means this angle right here is 90 degrees. We are only ever going to do this for parallel wires, so it's always going to be 90 degrees. Sine of 90 is 1. Okay, so we will often just see this force written like this, mu naught I1 I2 L over 2 pi r. Sometimes people put the L, like they'll take this L, where's my pointer, this L, sometimes they'll put it down here on the bottom, so you'll see force per unit length is equal to the rest of this. It might be like that on your equation sheet. This force, we kind of derived it looking for the force on 2, but by Newton's third law, the force on 1 would be the exact same magnitude. We'd have to figure out directions. They're going to be opposite directions, but so typically the force is going to look like this. Now I can go ahead and sub in here. So to actually solve this question, we kind of spent some time deriving this equation. I'm just going to sub into this equation. So mu naught I1 I2 L over 2 pi r. And we can say the force acting on either of the wires, because remember by Newton's third law, it'll be the same. Force is mu naught, which is, what is that, 4 pi. Where do I have it written? 4 pi times 10 to the minus 7, there we go. Should know it after all these years, but sometimes I forget. Current 1 is 4, current 2 is 4. The length of each wire is 4. Okay, a lot of 4s here. There's not always all 4s, but that's I1, I2, and then the length of each wire. On the bottom, 2 pi, and then r is the distance between them in meters. We multiply all that out. We're going to get approximately 1.3 times 10 to the minus 4 newtons. Okay, so this is kind of the magnetic force on each wire. We also need a direction. Okay, so let's go back and see how we came up with this stuff. So I focused on wire 2 for the force, which means I have to know the B field for wire 1. We figured out the direction of that B field right here. That B field is what's going in right over here. Okay, so using this thing here, this is right-hand rule number 3. The current of wire 2, again, this is conventional current, is going straight south. So I'm going to point my thumb straight south. The B field is straight into the screen, so the fingers of your right hand are pointing into the screen. The force then is going kind of this direction right here. I would say that is east. So the force is pushing east. By Newton's third law, this is the force that 1 puts on 2. By Newton's third law, you'd say, well, the force that 2 puts on 1 then is in the exact opposite direction. So these two wires are pushing each other away. So you could say away from each other. So the force on each wire is that magnitude, and they're pushing each other away from each other. Wire 2 is pushing 1 away, and wire 1 is pushing 2 away. And that's it.